So from our NMR, we ended here, but we'll kind of go through it. Again, I've been watching people go through and solve, and almost everybody jumps to the multiplicity or splitting to do some kind of understanding or interpretation of a spectra. It's not that that is per se wrong. That just happens to be the most difficult thing to analyze in HNMR. So if you jump to that point, you would better be confident in every other analysis. Okay. Maybe, what do we got, 29 people in here? I would say maybe 3 or 4 people are confident enough or competent enough to jump to splitting and ignoring everything else. Right? That's 3 or 4. Very, very small percentage of you. So don't look at the splitting first. Work through the rest of it. Okay? Starts with the number of signals. Okay? How many signals show up? This gives you information about the number of unique hydrogens or carbon if you're looking at carbon NMR. Okay? Chemical shift. Okay? Because we're looking at a hydrogen or a carbon magnetic moment, the chemical shift is now saying what things are around it. Okay? It gives us a rough local environment. So if there's more electrons present, that is going to affect how the magnetic field affects our hydrogen or carbon, and it's going to cause it to shift to a different value. So we can look at the ranges within our HNMR and our carbon NMR to come up with some kind of bulk classifications on what our group should be attached to. Integration will give you the ratio of the unique hydrogens only. So you got to be careful with this. It is a ratio, not the exact number of hydrogens. Okay? Sometimes it's straightforward and it is the exact number of hydrogens. Sometimes it's not. Okay? The times that it's not, because of symmetry. So you have to watch out. Sometimes symmetry shows up in our molecules. That will complicate or potentially overly simplify your spectra to make it more difficult. And then the last thing, actually before we even do the last thing, our integration will only apply to hydrogens. Okay? We'll avoid looking at carbons. Any ideas why we'll avoid looking at carbons? Carbon signals, percentage-wise, much, much lower than hydrogen. When we're looking at our hydrogen NMR, we're looking at hydrogen. Well, hydrogen makes up 99% of all of the isotopes for hydrogen, protium. Okay? That's the one that we're actually detecting. When we move to carbon NMR, we're looking at carbon 13, which makes up about 1% of all of the possible carbon. We don't get enough carbon in there to do some weighting information with our integrations. Okay? Too random to do any effects on, so don't look at integrations when it comes to carbon NMR. The next part is our splitting, which is the most difficult to analyze. Okay? So be cautious analyzing that. The other thing you have to be aware of is that there are multiple analyses that can come out of the splitting pattern, which means if you go through to compile your pieces and it doesn't work, more than likely you made a mistake in the splitting pattern. So go back and try a different way to interpret. Okay? That reiterative process can be difficult, okay? But it's sometimes necessary. This gets us our number of different hydrogen neighbors. Okay? Every hydrogen atom is a nucleus, okay? Is a small magnet. If I bring multiple small magnets near each other, do they have an effect? Yeah, that's what we're looking at. Okay, that's what's happening within our splitting. Okay, are also known as multiplicity. So, number of signals. This gives us the number of unique atoms. Okay, I've been noticing a lot of people panicking or not processing this quite well, and that's because when you look at a structure, you're looking at a two-dimensional drawing, and you fixed it, and it's now frozen in that position, and you can't do anything to it. Okay, that's completely not true. Your molecule is constantly moving, rotating, and spinning. So as a general idea on trying to determine the number of unique atoms, build your molecule. Okay? Point to an atom on that molecule. Close your eyes, toss the molecule, spin it around a whole bunch. Can you point to the exact same atom again? If you can point to that exact same atom again with 100% confidence, okay, then it is solely unique. There are no other hydrogens like it. If you get it confused with another hydrogen, what does that mean? It's not unique. And now both those hydrogens will show up at the exact same chemical shift, okay, which becomes relevant when we look at our integration. Okay, so every hydrogen gets counted. Okay? Where it shows up becomes our chemical shifts and our integrations and all of that. Okay? So if they have the same chemical environment, they show up in the exact same place, which means you only see one signal. Okay? There are some terms that get floated out there. I'm not a big fan of mentioning these terms because I find them exceedingly confusing and so esoteric in their reference that it's pretty useless. Okay? Your textbook, actually I'm not positive if your textbook actually references them. Okay? But you might see these terms float out there. Homotopic, enantiotopic, and diastereotopic. Okay? Why these ever get mentioned, I have no idea, but that's just the way it is. Okay, so let's kind of look at this. Whoops. Get an eraser in here. Let's draw on some hydrogens. Okay. These hydrogens are said to be homotopic with each other. They have the exact same chemical shift. Okay, we can't differentiate between them. Okay, so because they have the same signal, they show up in the exact same spot, we don't have to worry about anything. Okay, so those are kind of our straightforward ones. But what happens if we go through to an enantiotopic? Let's see if I can do this right. No, in fact, I think I actually had those backwards. Our hydrogens out here will be referred to as our homotopic. Our enantiotopic. These hydrogens are said to be enantiotopic. The reason being, let's go through and pick one of them and substitute it, stupid eraser, with an X. Okay. What if I'd gone through and done the other substitution? What is the relationship between our red and our blue hydrogens? They're enantiomers. These are said to be enantiotopic. Okay, so now we've defined them. Great. What does this mean? Jack shit. Okay. They get the exact same signal in the NMR. Okay, we can't tell the difference between them. Okay. The next part comes down to diastereotopic, which becomes a little bit more relevant. In our diastereotopic, what we're going to do is reference now this position. Same idea. We'll go through and we'll sub one out for just some atom X. And we look at our result on the other side. What is the relationship now between those hydrogens? Those two structures are diastereomers of each other. Okay? Those hydrogens see different environments, which means different signals. Okay? And you should be like, well, when does this matter? Well, how did we even start to evaluate the difference between our diastereotopic hydrogens? When did it become relevant to look at? What is consistent between these two structures? Not just that it's chlorine, but okay. And I would actually argue, I don't care about the chlorine. I have a stereo center. As soon as we have a stereo center, this destroys our spectra. And depending on the quality of the magnet or the instrument that we're using, sometimes we'll be able to differentiate between those hydrogens. Okay? Why would we be able to differentiate? Because they're seeing a different environment. Okay? If we go back to our original drawing, the red hydrogen, when it looks to its upside, sees what? What is on the up face of this structure? Chlorine. If the blue hydrogen looks to its downside, its up face, what does it see? Hydrogen. Is hydrogen and chlorine different? Yeah. So the red hydrogen and our blue hydrogen see different environments, which then means different chemical shifts. So this structure could show how many different signals? 5 different signals. Did I count that right? I think I counted that right. We have 1, 2, 3, 4, 5 different signals. Okay. For those of you being like, didn't we solve a problem like this? Yeah, you did. Right? Those of you that went through and did the spectroscopy packet, you solved a very similar question with this, where it was bromine instead of chlorine, I believe. And I think this was the exact structure. Did you see some weird complex splitting come out of it? No, you shouldn't have. Shouldn't have? Okay. That's fine, you can mock me. The reason being is that there was not enough difference to actually detect this. Are they still technically different? Yes. But when we look at the spectrum, all we end up seeing are 4 signals. Does this make things a lot more complicated? Yes. Go through and look at the spectra packet that you've been assigned. Go through and look at all the spectroscopy that you can find on the internet. You will find that the vast majority of the problems that you are told to solve do not involve chiral atoms, because it makes it vastly more complex and difficult to interpret. And we'll see that because it gets further compounded when we move into the splitting factors, okay, or our multiplicity. It's coming back to this idea of diastereotopic hydrogens. Okay? I want you to be aware of the term, have some general context of what it means, but that's about it. Okay? Its applicability to our class is pretty limited. Questions on what's up there? Yeah?
Would we see this on the final of the iPad?
Nope. ACS won't even test on it either. Yeah.
Will they test on the terminology?
They won't even test on the terminology. Yeah. Chemical shift. I wish I had some prettier pictures to show up here, but all I've got here are the notes that I need to draw. So actually, let's test you on nomenclature. I know this is nomenclature on things that you may not know how to name, but you've got the basic rules on how to go through a name, so see what you can come up with for the structure of these 2 compounds. So there's our 2 structures. So when we go through the name with our esters, we'll always put a substituent out front. So in this case, it's our ethyl or our methyl. And then we follow that up with the O8 or the ester part, which is our carbonyl-containing compound and the oxygen. The oxygen is where our substituent will attach. Acetate's a bit obnoxious. This is one that you're sort of not responsible for. Okay, the issue, because acetate is a common name, not IUPAC. Okay, that said, you'll see acetic acid, you'll see ethyl acetate, you'll see that acetate name show up a lot. You are going to be held responsible for knowing that common name. Okay, so the acetyl group is really this. When we make it acetate, we include that oxygen. Okay. If we then go back, oh man, I gotta step all the way through that. If we go through the methyl propanate, or propanoate, our methyl is our substituent, and then we have propanoate. 1, 2, 3 carbons. So that one we at least followed IUPAC rules. That includes our ester functionality within it. Okay, so those are our 2 structures here. If we went through to look at the number of signals, okay, what would our number of signals be for each of these? For hydrogen, sorry, good call. So our ethyl acetate gets us 3, And our methylpropanoate gets us also 3. Okay? So the number of signals is not different here. Okay? And in fact, if we go all the way through all of our possible connections, there is only one place where a difference appears. That one place where the difference appears is the... No, splitting will actually come out the same too. There is no fingerprint because this is HNMR. But if we take a look at the caption of the slide,
Like how close it would be.
it shows up to chemical shift. Okay? Where are your signals going to shift when we look at our spectrum? Okay, so our chemical shift tells us something about the local environment of our hydrogen signals. So if we go through and look at these, our hydrogens are connected to carbon all the way through. So we might predict initially that they would all have the same chemical shift. Okay, but there is one big distinction here. That big distinction is realizing what our chemical shift is affected by. Okay? The more electrons around our structure, the smaller the number, or the more upfield? I think it's upfield. I always get that one backward. But smaller numbers, that I get right. Okay. The closer it is to an electronegative element, what happens to the electrons? They get sucked away from our atoms. Well, if they don't have electrons around them, what happens? They no longer have their electron shield, which then means they become de-shielded and they shift to higher chemical shift values. So if we go through and take a look at ethyl acetate, which signal would we expect to have the most de-shielded position? The CH2, because it is directly connected to oxygen. The third one, we might say, oh, that's starting to get pretty close to the oxygen, but remember, we have to go first through that other carbon. So our CH2 and our ethyl acetate should be the most de-shielded, largest numbers, most downfield. Okay? I know I just threw out a ton of literature at you. Okay? But all of that accumulates. So we would expect our CH2 to have our biggest chemical shift, and I think we use the delta symbol for our chemical shift. Okay? What happens when we look at our methylpropanoate? We expect the methyl group to now have our biggest chemical shift. Okay. This is nasty, because if you were to go through and solve your spectra, you will find that you will probably end up with these two possible structures as ways to connect your pieces. Telling a difference between them comes down solely to your ability to interpret the chemical shift for either the methyl group or the methylene, that's CH2. Not easy to nail down. However, it is a super common ACS question. Okay? So watch out for that issue on deciding where your chemical shifts should fall. How would we tell the difference between the CH2 and the CH3? Well, number of signals. CH3 has more signals, but those more signals all show up in the exact same spot. Okay, so that doesn't help me out. The CH2 has two signals, but again, they all show up in the exact same spot. So the number of signals, I can't tell the difference between the CH2 and the CH3. Okay, chemical shift, well, the CH2 shifts bigger for ethyl acetate, or bigger for CH3, but how would I know it was the CH2 or the CH3? Integration. How big is the individual signal? Look at that. Segued and everything. Okay. The integration gives you information about how much or how many hydrogens appeared in that individual signal. Okay. How is this going to affect our signal? Well, if we just look at a counter, okay, I got hit, I got hit, I got hit. We start counting those positions, right? And we could look at a taller peak. Okay, just like we did with mass spec. However, if we take a look at our HNMR, is it just peak height? What else is happening? Okay, we can get the number of peaks within our signal, which then means our signal starts to broaden. As it broadens, what happens to the area underneath the curve? It increases. What does that necessarily do to the peak height? It brings it down. So when we're looking at the integration, it is the area underneath the curve which is determined by two factors, peak height and peak width. Okay. This is why when we look at integrations very typically, that information is given to you in some interpretable fashion. That said, the ACS has not developed to that level, and they really only expect you to look at peak height. Okay? So if we were to look at an individual spectra like this, we would try to come up with some information on how our integration stuff is supplied. So take a guess. Okay. We have one signal massively taller than the others. Okay. How many hydrogens do you think are represented there? A lot or a little? Okay. How about between these two? About the same, but less than a lot. Okay, and I'm going to pretend there's a space when I wrote a lot, in case there's an English major in here. All right, last one. Ah, I like the way you think. That height is about the same, but it's skinnier, which means less than everything. Okay. In a multiple choice exam, you now have some information. We have one hydrogen signal that is more than everything else. We have one hydrogen signal that is less than everything else. And we have two hydrogen signals of roughly the same thing. Okay. That on its own allows you to then interpret the multiple choice. Okay. We can add some more information to this within our guessing. We're typically looking at carbon structures, so what would have a lot of carbons? Or sorry, the other way, a lot of hydrogens. Methyl groups, which means we have 3 hydrogens. That's the only way we can get a methyl group, right? Okay. How do we have less than everything? 1 hydrogen. Why'd you not say 0? Because it shows up in the spectra. Okay? You know there's a hydrogen. What is somewhere in between 1 and 3? 2. So we now have information about our integration. This gives us our reduced ratio. This does not mean that I have a total of 8 hydrogens. Okay? I could just as easily have said that last one was 6 hydrogens. But what does that mean the 2 H's are? 4 hydrogens. And the last one is 2 hydrogens. That gives me the exact same ratio. Okay? And this is where integration becomes tricky. It gives you the ratio, not the number of hydrogens. Okay? How many people are happy interpreting integration with these height peak things? Really happy with it? Okay, well I won't worry about doing any other explanations. No, just kidding. I think that's a bit nonsense because you should actually have some more data, because in the real world you have more data. When you run the spectrum, you have a computer and you can tell the computer, tell me what the area underneath this curve is. And it'll spit out a number that's probably something ludicrously weird, 2,362.89. Like, well, that's not very helpful. Okay, but then it'll also tell you the area underneath these. Oh man, I picked bad numbers. The area underneath that one is 4,713. Is that close enough?
Yeah.
4,732. And this last one, anybody want to guess on that one so I don't have to do it? It's 3 times, right? So 6,000, 7,000, 7,080. I heard that. Okay. Well, that's a bunch of crap, but that's what the integration is. It's just the area underneath the curve, and that's how it calculated it. So what could we go through and do with this data?
Doing a ratio.
Turn it into a ratio, because that's all your integration information is. So what should we do to turn it into a ratio? Divide everything by the smallest number. And what ends up happening? We get our 1, 2, 3. Okay? And that's if you're being lazy and just having the instrument spit out the numbers for you. Okay? Typically what you would go through and do is on your spectra, you would tell it to integrate that area. You'd say that area is 1. Why do you know that area is 1? You ran the spectrum. Would you run the spectrum of an entirely unknown compound? Probably not.
Yeah.
You're probably running it on something that you made. So theoretically, you know what you made. There might be a 1 hydrogen signal in there. So you would tell it to integrate that to 1. What does it then go through and do? Calculates the ratio for you. And we end up with 2.06, 1.99, and 3.3. Does it ever come out perfect? No. But is that close enough where you can now interpret it? Yeah. Okay? So that's what you would expect to see in the real world. What do you see in this class? Well, I'll go through and tell you 1, 2, 2, 3. I've removed some of that kind of sloppiness in the numbers, but I'm giving you the same ratio. Okay? Is that the number of hydrogens? No. Okay? It is the ratio. The other thing that you might see me do, 1H, 2H, 2H, 3H. What am I telling you? I'm actually telling you how many hydrogens there are. Theoretically, I'm not giving you the ratio now. I'm actually telling you the number of hydrogens. I have been known to screw that up. Okay? But if you see the H symbol in there, I'm actually telling you how many hydrogens are present. This can also help you interpret our very first step, which was the number of signals. There's lots of peaks, right? The peaks aren't your number of signals. The groups of peaks are your number of signals, but where are your groups? Here it's straightforward, but what if there's some overlapping? I might go through and tell you where they are to help out with that. So you can look at that integration information to help you interpret how many signals there are. The last way that you could potentially see things, which is really, really ugly, but this is the way it used to get done, you'll see this line slide across the spectrum. What is this line showing? It's the integration curve. Okay? So the really old-fashioned way to do it was to cut out this section and then stack it over here to count how many times it repeated, how many times it repeated, how many times it repeated, and then you would say that first section was defined as 1H, and you figure out your other things. I don't know why people cut it out, because we have a handy-dandy, useful device that doesn't involve cutting. A ruler. Stick a ruler on it, measure the distance, calculate it that way. Okay. I've even heard people cutting it out and weighing the paper, okay, to figure out the ratio and the weight of the paper. Okay. Still technically works. Okay. So a bunch of different ways that you can see the integration information. It gives you something about the number of hydrogen in an individual signal. Okay? Questions about integration? Okay, now to everybody's favorite. Multiplicity. Okay? This is talking about your number of neighbors. Okay, so let's break this down. And this is a skill that you guys should be able to pick up. Not just going from spectra to compound, but going from compound to spectra. So let's start with our hydrogens. Why am I showing a different color for each of my hydrogens?
These are different signals.
There are different signals, so that can help me go through and do my interpretation. Okay, and we're going to start this one simply at first, and then we'll make it more complex in a second with that signal information that we talked about earlier. Okay, so let's start with our red hydrogens. Okay, chemical shift.
Less than 2.
Okay, we might predict less than 2 because that's our standard range for our alkanes, and we know that because we've memorized that information. It is kind of close to that chlorine being nearby, so it might shift to the higher end of that 2 range, but it's still probably in that less than 2 range. Okay. Integration. Integration, how many hydrogens are just like it? 3. Okay, how do we know that?
3.
Okay, we can kind of cheat and say I already color-coded it, right? There's 3 red hydrogens. Okay, but how do we know those 3 hydrogens are all chemically equivalent?
They can be confused with each other, but not any.
They can be confused with each other, but no other hydrogens. How do we know that? A lot of that comes from building the model and seeing that their relationship is completely confusing with each other. Okay. So what I would then tag now is I would say I would expect a 3H signal for that. How about the next one, the blue one? The 1H signal, the purple ones. Black ones, 3H. Which of those 4 signals should have the highest chemical shift? The blue one should have the highest chemical shift because it's closest to the electronegative chlorine. Okay. Where would I expect the red and the purple to be? In between the red, or sorry, the blue and the black, yeah. What else? How different are the red versus the purple as far as their chemical environment? Not very, which means their chemical shift should show up pretty darn close to each other. That may make it difficult to analyze later, but that's something that we can at least flag as information. Okay. Now how about the splitting? Okay. Our splitting has to do with our neighbors. Okay, so multiplicity or splitting. It's all about neighbors. Okay, and in particular, unique neighbors. Not like that normal one next door. Okay, that crazy, weird, loopy one. Okay, those weird neighbors now will affect our signal. Okay, so if we look at our red hydrogen, we want to count neighbors. So the first thing we need to do is recognize this 3-bond rule, okay, which I'm going to put in quotes until we fix it. Everybody seems to remember the 3-bond rule and quote it like the Bible. Okay? It's not 3 bonds. It is actually a little bit less defined than that. It is less than or equal to 3 bonds 99% of the time. Okay? So let's count out our 3 bonds. Let's see, is green going to work on this? No. So for that red one, I'll count in blue bonds. So I'm starting from my red box, and I want to count out bonds. So I go out, there's 1 bond. All right, everybody see that? So we go out 1 more. That's a 2nd bond. What atom am I at? A hydrogen. This could now potentially count as a neighbor as long as it is unique. Is it unique? No, so it can't count as a neighbor living in the same house. Okay, so we'll go back. There's our 1 bond again. We'll try out again. I'm at another hydrogen. Is it unique? No, so I can't count it as a neighbor. So I'll do a 2nd bond. What atom am I now at? Carbon. Carbon does not count as a neighbor. Okay, it has to be a hydrogen, so that doesn't count. So then I go up 1 more bond, and I'm at chlorine. Is chlorine a hydrogen? No, so that doesn't count. I'll go out 1 more bond, and I'm at hydrogen. Is that hydrogen chemically unique from the red one? Yes. I have now found a neighbor. Okay. I will continue to go around through the rest of the structure to test this. So I'm at 2 bonds to get to this carbon, right? So I go out 1 more bond. 3rd bond, I'm at carbon. Is carbon hydrogen? No. 99% of the time, I'm done. Okay? So that's where I would stop, which got me how many neighbors? I have 1 neighbor. What is this going to do to my signal? Neighbors plus 1 equals the number of peaks, which means I have 2 peaks, also known as a doublet. Is this straightforward? Everybody's okay with it? And I shouldn't go through and do it with all the others? Or let's try it this way. You guys do blue, red, or what is it? Blue, purple, and black. Do it in the next 4 minutes, and then I will go through and write my answers over the top. Okay, there are the answers. Everybody get the same thing? Any questions? As long as everybody's on the same page, I will move on and make it a crap ton more complicated, which is back in that splitting a splitting thing.
More complicated.
Okay, so as long as everybody's good, okay, we'll move on to the next layer. And a couple people asked about this. When we look at the purple hydrogens, were they technically the same? No. If you go back to the number of signals, remember we said that those hydrogens are diastereotopic, which means they are different from each other, which means we get 5 signals, not 4. Is that going to mess with our splitting patterns? Oh, yeah. Okay. And that's where we'll end up kind of spinning into this side topic of splitting. Okay. So let's go at it simply first. We'll start with our blue hydrogen. Okay. So this is what we would expect to see in our spectra, or what we would probably see in our spectra, is exactly what's written up here. Okay. The theoretical spectra becomes a lot more complicated. Ah, I did not want to erase that. Thank goodness I have an undo. Okay, so what do we end up having to do? So let's take a look at the blue one. We'll start with that on what's actually happening. So theoretical. When we look at the blue one, to the left we see 3 red hydrogen neighbors. To the right we see 2 purple hydrogen neighbors. Okay? And in this analysis, we group those together into a total to say 5 neighbors, which gets us 6 peaks, okay, based upon our rule patterning. Okay? But are the red the same as the purple? No. And this is where things can kind of snowball into hell. Okay? If our magnet, if our instrument is strong enough, what it can do is detect the difference in the splitting between the red versus the purple. Okay. So what we're saying is that the red hydrogens will split our blue hydrogen to give us a new signal. The purple hydrogens will then split the new signal. Okay. So let's ignore the purple hydrogens for the moment. Okay, we start with a signal for our blue hydrogen, okay, just to start off with. We then affect or bring in our multiplicity with our red signal. So our red neighbors, there's 3 of them, which means how many peaks should that blue 1 signal become? 4. So it splits into 4 peaks. Okay. Interesting thing to note here is the pattern behind this. You'll notice that in all of our splitting patterns, they are symmetrical. This is a requirement for splitting. Okay, they will always be symmetrical. The only time they're not symmetrical is when you have multiple signals overlapping. Okay? Does that make it more complicated? Yes. Okay? Watch out for it. So that would be if we just had the red neighbors, but we also have the purple neighbors. Well, the purple neighbors says what should happen. Well, there's 2 purple, which means I need 3 peaks. So this signal that we now have is in red. That must now be split by our 2 purple neighbors. Okay? So let's start. 2 purple means 3 peaks. Laughter's kind of the standard response to this. What just happened? This split into 4 peaks because there's 3 neighbors. Okay? And that's why we saw 4 peaks, because I started with 1. I split the 1 signal into 4 peaks. What happens in the next step? I'm splitting 4 peaks into 3 because of the 2 neighbors. The result ends up being this complex, nasty-looking thing. Okay? This is what's known as splitting of splitting. What happens if we use a really weak instrument? Well, in a really weak instrument, we can't differentiate splitting, which means what do I see? I see 4 signals, total, okay, for the whole compound. The signal I see for the blue one is 1 signal. I see nothing else. As I increase the strength of the magnet, it's now allowing me to differentiate those different signals, or the splitting effects, and it can now start to turn into 4 peaks. As I continue to increase the strength of the magnet, it now differentiates the splitting of the splitting pattern, and it splits even further out into this big complex mess. Okay? What do we end up seeing? Okay, well, the visual result is what we summarized already, was 6 peaks. I can count. Did I count that right?
Yes.
Yeah. There's our 6 peak signal. How did we go from this big, nasty, ugly thing to a relatively nice, organized 6 peaks? This starts to overlap. This starts to overlap. Those signals happen to overlap in such a perfect fashion that what do we end up seeing? Just 6 total peaks. The theoretical aspect of splitting means we get our final purple line. The actual aspect of what happens when we look at most splitting, that's our black summary that we all predicted to begin with. You are responsible for acknowledging both. You need to be able to solve, and you need to be able to understand the theory on where it's coming from. The theory is what's referred to as splitting of splitting. Again, under most circumstances, those signals overlap. As they overlap, what happens to the area underneath the curve? It increases, and I start to see the splitting patterns that come out of the other one. Okay? You don't have to like it, but that's the way it is. Okay? That was now our blue signal. So could we come up with a description of this so that we can actually name it? Because with 6 peaks, we could call that a hextet. Can we really call that a hextet? That big old nasty multiplicity thing? No. So there's 2 ways that we can reference it. Number 1, we could just call it a multiplet, which is, I give up, I don't care, I'm not counting it, it's a ton of peaks, deal with it. Okay? Fair enough, that happens. Theoretically, you have to be able to name it. So, what happened?
4
We have 4 peaks, so we have a quartet of triplets. No. I'm not even sure what you said, but no. No, it's not that. It's a quartet of triplets. Okay. This is allowing us to differentiate that on one side we have 3 neighbors, on the other side we have 2 neighbors. Is this more structural information? Yeah, this is a heck of a lot more than if we just said 5 neighbors. Okay. Getting very, very specific. The odds that we see something this complex, fairly rare. But it does happen. When does it particularly happen? Chiral atoms. You throw a chiral atom into the mix, the whole thing becomes a fun show. Okay? Questions on that? How does this mess with our purple signal? Okay. In our theoretical aspect, how many signals were in our purple signal? Were those the same hydrogens? They were 2 different hydrogens. We have HA and HB. How many neighbors does HA have? It has the 1 hydrogen that's in blue. It has the 3 hydrogens that are in black. And lucky us, it also has our purple HB. Because they are diastereotopic, which means our splitting pattern becomes splitting of splitting of splitting. Yay! Okay. This is one of the big reasons why we don't include chiral molecules when we go through and solve. Okay. What would HB look like? Same thing, but different. That kind of works. We just exchange HB for HA. Okay. Depending on the structure, sometimes you see this, sometimes you don't. If you look at the spectroscopy packet, number 4 shows it, 4 shows it, and 6 shows it. Shows this complex, nasty splitting of splitting. What I expect you to be able to do is give me the theoretical aspects of it. I do not expect you to be able to solve them. Okay? Questions about that? Yes?
I'm just kind of getting confused where you got the name of quartet and triplets.
I'm glad you asked that now. So if we start with our blue hydrogen again, we had one signal that represented our one hydrogen. What happened to that signal? It was split by our 3 hydrogens, which gave us 1, 2, 3, 4 signals. There's our quartet. That quartet was then split by our purple hydrogens, which was 2 neighbors, which gave us triplet, 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 and a triplet. Whoops, that one needs to be shorter. And we have our quartet of triplets.
Question. How do you know which one to go to? So why didn't you split that one signal into 3 signals?
Why did I not split it as a triplet of quartets? Good question. How would you know? Experiment. That's it. You'd have to go to the experiment to see. It's going to be based off of whichever splits more strongly than the other. Right. That is you're going to see in your spectrum. I don't expect you to be able to predict that. Madeline, does that get you your quartet of triplets? Okay. Or technically our triplet of quartets. Is a triplet of quartets going to look the same? No, the patterning is going to be all slightly goofy off of it, but it gets you the same general idea. Okay? Don't look too excited. One question. Okay? Another big common place where this shows up. Come on. Oh, it did it. How many hydrogen signals? One, 2, 3, 4. Because there's a double bond, can I freely rotate? Nope, which means this hydrogen only sees the CH3 directly across from it. The other hydrogen only sees the hydrogen. Are those 2 hydrogens different? Yep, you get 4 signals. Where does this become even more fun? Let's count the neighbors for that now purple hydrogen. It has 2 neighbors, so what's the splitting pattern? A doublet of doublets. Why? The blue hydrogen is different from the red hydrogen, which means they split differently. This is probably the most common place that you'll see complex multiplicities. Okay? Terminal double bonds. Okay? And it almost always shows up as a doublet of doublets. Okay? Don't have to be happy, but you have to accept it. Questions? No, it won't see the CH3. Why will it not see the CH3? If we count out our bonds, and this is actually a good example for the next thing, there's 1, 2, 3. I'm ending at the carbon. Okay. Remember we said it's not the 3 bond rule, it's the less than or equal to 3 bond rule that works 99% of the time. Where's that 1%? Typically around double bonds. Why around double bonds? They're shorter, which then draws those hydrogens a little bit closer. So you can sometimes skip 3 single bonds and a pi bond. Can get you into a splitting range. How often does that happen? Very, very rarely, but it does pop up. Okay. Other questions? Could be worse. There's reference to a coupling constant in your textbook. I don't want to spend a whole lot of time on it. That coupling constant is referring to the distance between peaks. So if we take a look at our D hydrogen, okay, where are its neighbors? It's the C hydrogens, and there are how many? 2 H's. So we would expect what kind of a signal? A triplet. So we see 3 peaks. Okay, so there's our splitting pattern. I color that red? Yeah. 1, 2, 3. And our C hydrogens see how many neighbors? 3, so we get 4 peaks. There's our 4 peaks. So we could say and be happy and be done with it. What the textbook is now referencing is if we measure the distance between those peaks, what is an interesting observation? Yeah. The distance between peaks, okay, is your coupling constant. How tightly are hydrogens coupling to each other to generate the splitting pattern? You can calculate that coupling constant, and you could go through and instead of saying kind of process of elimination match things through your spectra, you could measure that distance, and then whichever other peak gave you that exact same distance, you now know they're coupled to each other. Okay. Generally, not super relevant. Where it becomes really important is if you wanted to say distinguish between, give me a sec here, erase this. What is the difference between these 2 signals? We're going to end up with the same number of signals, which will be actually, I need to add another carbon in there. I have to. Same number of signals. Chemical shifts, same. Integration, same. Splitting pattern, same. So how would we tell the difference between these? If we take a look at the hydrogens involved on our double bond, do they see each other differently in the structures? Yes. If they see each other differently, what changes? The coupling constant. We can tell the difference between these 2 structures in the spectra by measuring the coupling constant for the hydrogens in the double bond. Right? I don't think I asked any questions on it in the SMART work, and I think I kind of left it at that, just because it is a very complex thing to look at, and again, fairly rare. Okay? So we might throw that back in as a kind of a pop quiz, random, fun thing, but we won't see that on this next test. Okay? But the coupling constant can help you decide which signals are being coupled to each other. It can also help you determine the arrangement of groups. Questions about that? Wow, that really depressed you all. I'm sorry. So there's some fun summaries that you could look at. So if we look at a trans arrangement, the coupling constant is 13 to 18 hertz, whereas if we looked at the cis, it's 7 to 12. So you can tell a difference between that coupling. Okay. Fairly rare to ever see that question pop up. The only times I've seen it is when someone's really trying to differentiate quality of students. Okay. like really, really trying. Like they're looking at the class and everybody's getting an A, so they're like, well, let's screw them over. Okay. I've not done that, just so you know. Feel free to test me, though. Questions on that? Okay. Guess what? That's all of it.